So, what this novel approach which I will present are based on new interpretation of electrodynamics of superconductors. And first of all, of course, Meissner effect. So I will start. Yes, I will start from brief review, reminding what it is about, Meissner effect and the Meissner state, and of course difficulties of the standard interpretation. Otherwise, there is no sense in introducing the new one. Yes. Okay. Yes.
Yes, sir.
So that's what the outline. I have to say immediately that all these things which I want to present is just recently published in pretty big review, 30-page review. So I will do my best to present this stuff, but of course it's physically impossible. So it will be some references, pretty many references to this paper. It is also, this paper, the reference is available in the abstract. So no problem. Well, so let's go to check what's going on with the Meissner effect. Meissner effect was discovered in two experiments, independent and different experiments, of Meissner and Kozhevnikov and Rybinin and Shubin. Meissner and Kozhevnikov measured field distribution around and inside in one arrangement of long cylindrical samples, one or two, in transverse field. Cooling samples down, that is field cooling. And they found that the permeability of the superconductor was 0, or diamagnetic susceptibility 1 minus 1 over 4 pi. So the field changed. It was not supposed to change if just superconductors are just perfect conductors as they were interpreted by that time. Rybinin and Shubnikov measured magnetic moment of the sample, long cylindrical sample, in parallel field, and also concluded that the actual fact that a jump takes place in induction in following the field strength, that is, data are presented induction versus the field strength, which is in this geometry equals to applied field. So we incline it as to ascribe to the formation of new phase with B equals 0. Important that in this arrangement, as well as in this too, no eddy currents can be induced at all unless the Faraday's law is broken. So the essence of the Meissner effect is at definite conditions, a superconducting sample can be found in a reversible, that is in thermodynamic equilibrium state, referred to as a Meissner state, characterized by zero induction simultaneously with zero resistivity. I don't know why it's not here, but anyway. So let's define what these conditions are. Let's check. So there are a few definitions of the Meissner state. Either this is a state in which induction equals 0 throughout the volume of a massive body in static field, or this is the state, thermodynamic state, in which magnetic susceptibility is minus 1/4 pi over the volume of the void. Meissner state is observed only in sufficiently pure, singly connected samples of ellipsoidal shape only. In this field range, where eta is the Mach factor relative to the axis parallel to the applied field. Important to remind that the Mach factor is defined only for ellipsoidal samples with uniform magnetization. On the other hand, in any ellipsoidal sample, that is, either it is homogeneous magnetization like it is in the Meissner state, or it is inhomogeneous equilibrium state like intermediate or mixed state, the field strength H or field intensity is uniform all over the volume of this sample. Now, due to that, yes, of course, Meissner state is impossible at eta equals 1. Just interesting point that superconductors with demagnetizing factor equal 1 do not exist. It was shown brilliantly by Maxwell in 1862. Well, so we can also define the Meissner state as a equilibrium superconducting state at which the field intensity H with magnitude less than Hc1 is uniform through the volume of the massive sample. Well, and one more important characteristic of the Meissner state, that due to thermal equilibrium, the Meissner state must meet the time reversal law. This is the law. Regardless, classical system, quantum system. Therefore, all currents in the Meissner state must mutually compensate each other, so the total current does not arise. Never possible. Okay, now let's look at the standard interpretation. Standard interpretation of Meissner state and more general electrodynamics of the superconductors is based on the London theory, with minor modification. This interpretation is adopted in PCS and in Ginsburg-Landau. You are well familiar with these formulas, but I will just remind that the London theory is based on two equations which are derived from the Newton's acceleration equation with three sets of assumptions. The first one is that superconducting, as they call it, electrons are free, spinless, and non-reacting on magnetic field. There is no magnetic field. Oops. Yeah. Another set of equations, of assumptions, is magnetic permeability and dielectric permittivity of the superconducting state is unity. This very strange assumption, equalizing, in fact, just equalizing properties of superconductors with properties of vacuum, was introduced as a kind of temporary simplification, which can be corrected, as Posser said later on. But 15 years later, in his book, Fritz London keep this assumption in force, and they have not been corrected any time later. Well, another set of assumptions is this one. The subscript infinity means quantities in the sample interior away from the surface. The first assumption is just a postulate based on the Meissner effect, and the second one is justified by never published Bloch theorem, but actually it directly follows from this time reversal rule. From these two assumptions, it also follows that h inside the sample, velocity of electrons inside the sample, vector potential are all zero. So superconductor superconducting material in this interpretation is totally inert inside, right? So the next steps, this equation, second London's equation can be presented in this form, where A is defined is this way, vector potential, right? And then it's easy just to convert this formula, just plugging in lambda L and opening J to this form. This is microscopical form of the London equation, which means that P tilde, that is generalized linear momentum, is zero. That's what London calls in all the range of the temperature and the field of the superconducting state. So this property Fritz London calls rigidity, and then using this rigidity for multiply connected samples, he derives this flux quantization. And it was real triumph of the theory when the flux quantization was discovered experimentally. And although with factor 1/2, which was missed in original prediction, which was interpreted by Zager that it is due to pairing, it is consistent with BCS theory. So London argues that rigidity is cornerstone of superconductivity, which offers remarkable possibility of reducing superconductivity to an apparently very simple model. Well, yes, one more point. London's, from the very beginning, understood very well weakness of the assumptions, the physical background of these equations. And so in the book of 1950, Fritz London did not derive these equations as they did it with his brother in 1935, but just introduced them as a kind of postulate, saying that validity of these equations is justified by experimental confirmation of consequences which follow from these equations. Well, let's check how this really is it really so. But before we go to say to issues of this theory, let me remind some formulas which follow from thermodynamic and solidly justified by experiment. This is magnetic moment of a sample in the Meissner state, and magnetic energy. This is very important term for which it is also very well shown. Even Guggenheim in 1936, and then Landau-Lifshitz also addressed it specifically, that by virtue of the energy conservation in superconductors with zero demagnetizing factors, that is cylindrical geometry, this magnetic energy equals to kinetic energy of the field-induced motion of electrons. This is energy conservation law. Well, let's look at the London's samples. In London theory, the sample, the active part of the sample is just thin surface layer where current and field are not zero, with effective thickness lambda, London's lambda. Yeah? All the rest, basically, not just majority, not just 99, but say 100 minus very small percent of the sample volume is totally inert. It is, if it is so, then there is no difference if this material is in S or in N state, or there is no this material at all. Well, on the other hand, the cylindrical, that is in the London theory, the sample of cylindrical geometry like that in parallel field is identical to just a long solenoid. In this long solenoid, if you set the current which is needed of this value, you will get field inside the solenoid which it will compensate each H naught, and there will be no field at all. Yeah? No B, no H, because mu is unit. There is one in solenoid. But on the other hand, solenoid is a particular case of a spheroidal current shell having shape of ellipsoid of revolution. So the same is applied to this picture. So can we say then that London interpretation correctly describes a Meissner effect, that is, B is really zero here and there, and B equals H, as they said, as they assume? No, of course not, because already Meissner effect is observed not only in spheroidal samples, in sample of this shape, but in any ellipsoidal sample. In particular, it can be like that, film in parallel field. According to the standard interpretation, the screening current runs in a thin surface layer along the surface, and the transverse cross-section of this current represents a rectangle with infinite aspect ratio. In this case, 5 millimeters over 3 microns. But how can electrons or pairs which are supposed to be free run along straight paths if they are constantly pushed sideways by magnetic part of the Lorentz force? How they can make U-turn without changing their speed and without breaking the law of inertia? Yeah? So, but maybe there are many more issues which were partially also addressed in that paper which I referred, but maybe the most clear thing is that coming from the boundary condition for magnetic induction, it's easy to calculate energy of single electron, kinetic energy induced in this and needed for this current. It will be this one. Then we calculate all kinetic energy of all electrons in this lambda L, in this effective thickness surface layer. That will be this one. And if you compare with that, it's much less. Of course, you don't need to do any calculations because the active part of the sample is only very thin layer, whereas this is volume of the sample. Yeah. So of course, so the point is that actually conflict of the London theory or the standard interpretation with the law of energy conservation, I am not the first, was mentioned already by Schoenberg. He paid attention that if your sample is spherical, then assumption of the screening current leads to appearance of kind of hole-like voltage between pole and equator. So you can connect these points by resistive layer, by the resistive load, and you will get energy for free, just pumping it from the stationary static magnetic field, as long as you wish. So, of course, it's something. And one more very interesting issue in this interpretation, that London theory does not mention at all the necessary condition of persistency of the current. This current is assumed, it is stated that it is persistent. That is indeed so in experiment. Yeah? That is quantization of angular momentum of charge carriers. So let's check how all these issues can be resolved. That's what it is, micro model. So this is a well familiar picture of field distribution near sample of, say, cylindrical or spherical. And according to London, this not only B, but H equals 0 also. This is what his assumption, and this is wrong. If the first picture was absolutely okay, this one is wrong. And that's what correct picture. B is 0, of course, but H is not.
What's the difference between your terminology H and B?
H is
H zero is external field.
No. H0 is external field, right.
Yes.
H0 is external field. This is the field magnetizing force, as Maxwell called it. This is the field which is B minus 4 pi I. I is magnetization, which we call normally field strength or field intensity. There are many names, but that's what UPAC recommends field strength, but I use field intensity. Anyway, how it can be now, what we can get from this picture. We start from Bohr-Sommerfeld condition, understanding that for single Cooper pairs, that linear momentum in magnetic field must be taken in generalized form. And in the ground state, and this is Planck constant and non-negative integer, n must be minimum, that is 0. And so we get in the at 0 temperature and 0 field, ground state. This one, it is pretty much looks like London rigidity, but so far it is just for 1 point. Now at 0 field, generalized momentum equals to just to kinetic momentum. So we have this. This is definition of the Cooper pairs. Yeah. As a correlated state of 2 electrons with total 0 linear momentum and 0 spin. 0 spin follows just from requirement of thermodynamics, because system of units with 0 spin has less free energy. Now, what else do we see from this equation? We see that center of mass of these 2 electrons is at rest, and two the spiral electrons are just orbiting the center of mass. Okay? As soon as it's so, they have momentum, angular and magnetic momentum.
You have
And
five,
one more
5
important-
minutes. You have 5 minutes. Yes, yeah.
Well,
Yeah.
momentum is zero and what? So, okay, so what will be next? When we turn on the field, they will certainly precess. Then either using Larmor theory or just considering Lorentz force acting on these two electrons, you will end up with the point that, first of all, this momentum, total sum of this original momenta is zero in any, without or in the field or without field, and the same for linear momentum. So far at zero temperature. Then from that, so what does it mean precession? Precession is the same undisturbed orbital motion plus additional motion in the plane perpendicular to the field H. Well, then the net effect of the field is induced current circular motion of the paired electrons in the plane perpendicular to the field. And then with this frequency, with this velocity, and radius of this circulation is 2 lambda L. And moreover, this radius doesn't depend on the field. Then, so it is absolutely the same as a standard diamagnetic. This is from textbook of Tam. Now, what about temperature? Temperature is okay. Yes, from this point, we immediately get all the properties of the Meissner state. We have momentum, correct. We have, of course, energy conservation, correct. We have gyromagnetic ratio, which was measured by my boss, Kikoyan. And induction is zero. It's for the first time induction is zero. In standard interpretation, this is just the postulate. Now, what about the temperature? Since all induced magnetic moments are parallel, all the whatever, they all are parallel. Entropy of ensemble of the Cooper pairs is zero. As soon as entropy is zero, temperature of this ensemble is zero regardless of temperature of the sample. In all range of existence of superconducting state, temperature and the field. So we may say that all three big zeros, superconductivity is characterized not only zero induction, zero resistivity, but zero entropy. You can go back to fluid model. So all they follow from the single or Sommerfeld condition for Cooper pairs. Well, this is not the only. There are lots of all properties of superconductors can be very easily open. In particular, how this current arranged with respect to each other. They make these wheels like solenoids with two constant, two parameters with dimension of lengths. This is R perpendicular, this is projection, RMS projection of this radius of orbiting radius of electrons and induced radius. So then we will end up with type 1 and type 2 with, when we have different relationship. Either this aleph is more than 1 or less than 1. You will get positive or negative surface tension, type 1 and type 2 superconductors. Well, you know, flux quantization is also there. And what is interesting here is that what is the vector potential of induction? We introduce vector potential of the field strengths. What about induction? This is microscopic average of the vector potential of induction of the vector potential of field H, determining the induced microscopic currents. That is exact match with classical definition of the vector potential. If you open the Tang's book, you will see it. And then flux quantization, of course, with correct factors and so forth. So all but one incorrect assumption about the field inside of the London theory follow from the quantization condition, provided that this J infinity and so forth are average of corresponding microscopic quantities. At the same time, this absolutely unrealistic assumption, unity of mu and epsilon, certainly, and assumption of circumference, that is assumption of screening current, gets away. Okay? Now, this is, I have...
This one, less.
Yes, this is total current. This is very interesting. So far we spoke about equilibrium states. And in this equilibrium properties are basically, they are caused by this induced current and by precession of Cooper pairs. But of course there is the same as in standard diamagnetics. However, there is important difference. In conventional diamagnetics, the orbiting electrons are bound to motionless atom, whereas Cooper pairs are movable. So we may have total current when Cooper pairs move. And then, so what is here is that total current and superconductor. So we have two types of current, exactly like in normal metals. We have bound and transport current. Here we have bound in Cooper pairs and transport current due to this total current. It is the same role as a transport current in conventional metals, but in conventional metals it is executed by conduction electrons, which temperature is very high, regardless of temperature of the sample, right? But here, the temperature of Cooper pairs, a symbol of Cooper pairs, is just 0. And therefore, because they obey Bose-Einstein statistics, they condense absolutely always. And so they make this Bose-Einstein condensate, which explains this zero resistivity. And so, but even in presence of the total current, this magnetic properties of superconductors are different than what it is expected for so-called hypothetical perfect conductors. The total current always accompanied by, it is a combination of translational and rotational motion. And this is in full consistency with original experiment of Meissner and Oshel. But you can read that when parallel superconductors were connected end-to-end in series, and external current is connected to flow through them above the critical temperature, magnetic field between superconductors increased below transition temperature. Why? Because they start rotating. Well, this was...
Maybe here.
Yeah, I will just say the most interesting. As soon as we have magnetic field, you have lots of probes to check what's going on there, to check, to measure microscopic properties. So far, the superconducting properties, it is huge headache because they are probed from the surface. And surface is as power is said is made by diyavol, whereas bulk is made by God, right? So, and we can probe bulk. And moreover, there is, I will skip that, but this diamagnetic resonance which follows from this. So we have, apart from a regular APR, resonance due to normal electrons, which are always present in superconductor. We have diamagnetic resonance due to this magnetic moment of orbiting electrons. And from that, we can, from frequency, we can directly measure the field strength H, which is not measurable quantity in the regular materials. From amplitude, we can get concentration, that is number density of Cooper pairs, and this magnitude will change with temperature. And relaxation time is the most interesting thing. It will be different, and it will reflect some specific of the Cooper pairs. Now, the samples should not be small, and now I will skip this summary, and I just want to say the main feature of the new model is striking simplicity. What can be easy? Model of such kind of was anticipated by Fritz London based on discovery of rigidity. And on the other hand, being semi-classical, of course, this model cannot and does not address specifics of the latest polarization responsible for Cooper pair. And these experiments, which are suggested, and I want to suggest them, there is a hope that they will help to solve this problem. So I want to say at the end that in this paper there are lots of references for this book, which I published just 2 years ago. And if you and I would strongly recommend. This is a book which addresses issues which are not regularly addressed in standard text. And so, if you are interested, I can give you.
Thank you. Some questions, please. Abdullah.
I'm a little bit confused with your notations of P tilde and P.
Yes,
Will you please?
P tilde is generalized linear momentum.
Oh, P
This is P
plus
plus
electromagnetic field. A.
P tilde is mv plus E over m times A. That's what generalized angular momentum, how angular momentum must be considered in magnetic field.
Okay.
That was London rigidity, that is for P tilde.
Another questions, please. Thank you. Another questions? Yeah, yes.
Thank you for your impressive and motivating presentation. So I will need some time in order to get more acquainted.
I'm very sorry. I said that. Please look at this paper. It is long, but it's nothing.
Now my question. It looks very natural to consider precession because we have charges in the magnetic field.
Yeah.
But your considerations, at least in this presentation, were based on classical theory of precession. If we consider Cooper pair,
Yes.
it's a quantum mechanical
Yes.
entity,
Yes.
which,
Yeah.
as you know, that does not consist of 2 points charges. There are wave functions of that.
Yeah.
Absolutely.
And in case if you calculate this same effect, really or hypothetically now, within quantum mechanical approach, would you obtain the same or similar, and how would it be with all your very nice exact correspondences, because they will depend on another part of the reality, I mean quantum mechanical nature of a pair. Thank you.
Yes.
Yes,
For
this is
example,
exactly
about the entropy. It will remain the zero or not?
Yes, sure. The point is that the Cooper pairs are heavily overlapped. Absolutely, of course. But we know this is how many electromagnetic waves do we have around us? Yeah, they all overlap. Billions. Yeah, but it doesn't mean that I can't see you or you can hear or see me, right? Everything is fine. This overlapping doesn't affect neither mobility nor stability of the Cooper pairs. That's what it is. The rest, of course, this is semi-classical model, but the essence is there. I am experimentalist and I don't care for the most. I will do the project to check this new effects which predicted, but I expect that earlier or later this quantum theory of this stuff, it's exactly as it takes place in regular diamagnetic. We have two formulas, classical Langevin formula for diamagnetic susceptibility and quantum formula. They're exactly the same. And the reason why they are the same is that in both cases,
I am sorry.
spin is compensated. Just one second. Spin is compensated, and therefore h, the Planck constant, does not appear in the final form.
Okay, thank you.
Thank you. After this one, you can continue in
Yes, sure.
in corridor.
Absolutely.
Thank you again.
Yes.
But it will be nice in the beginning you explain motivation of this study because of maybe any experimental results, maybe any indications, the absence any exact moments in this theory. But you are starting directly from these equations and why these equations is.
I started from what it is Meissner effect, and I shown immediately on the first slide that the screening current cannot appear in the Meissner effect.
Yes, thank you again.